Swayam Prabha. Digital India. Educated India.
Good afternoon. Welcome you all to this concluding lecture in this particular course on analytical, spectral and microscopy applications of inorganic compounds and nanomaterials. So we have had the lectures in this particular course on analytical methods, a number of analytical methods. So, and those are something like atomic absorption spectroscopy, the chromatography based things, just very simple aspects of that. And then we have thermal methods also coming into. In the thermal methods we have treated quite several number of different ones. Later on I will just bring a recapitulation of all that to you. And electrochemical methods and magnetism in the inorganic compounds. Of course, entire this course is focused towards the inorganic compounds and nanomaterials. So even if I have not written in the title inorganic, that does not mean not for the inorganic. So in this whole course I have treated 4 topics under these the analytical kind, and then we have 9 different spectral methods have been covered. And for example, absorption spectroscopy, fluorescence spectroscopy, mass spectrometry, EPR spectroscopy, XPS spectroscopy, Moss-Bayer spectroscopy, and XANES and EXAFS, and the inorganic NMR spectroscopy, vibrational spectroscopy. So all of these, each of these we have spent quite a much. Just tell you, in each of the case I used to give one basic thing, some simple principle level, and in some cases a little bit instrument, but not instrumentation, instrument at principle level, because that will give an idea how to measure, what to measure, etc. And then the rest of the thing entirely covered on taking up examples and interpreting, taking up the examples and explaining the things. And that is how the model that I have taken up. And towards the end I have always proposed certain kind of exercise so that one can develop their own attitude to understand, learn and enhance their knowledge based on these things. Then also at after finishing all these spectral techniques, I have taken the diffraction techniques, of course focused primarily on the powder XRD with some features given for crystallography aspects. I won't claim a large number of crystallography features are given in this course because that is not required, becomes out of focus of this, because this is meant for application type, primarily helping the students at the master level, at the PhD level, and those scientists, technical people who are working in industries with these equipment and in chemical analysis, structure determination, identification compound, identifying the impurities. So these kind of purity of the compound, all those things. Then the last part of the thing I have done this particular microscopy methods. In the microscopy I have done primarily the AFM, SEM and TEM, not though planned earlier to do for a few other like fluorescence microscopy and the laser microscopy kind of things, but could not be covered into this because that becomes too huge packed into that. Okay, so main thing is, since I have focused this course towards the application orientation, I have taken examples from a lot of papers, particularly of the somewhat recent origin in these things, which is very easy to get from the internet space, and then try to explain to the extent required for that particular technique. Because many of the papers, if you go and open, you will find half a dozen techniques or maybe a 10 different techniques on the same system explained. But here I have taken up only that corresponding to that particular technique. What is the kind of information? How would you support that technique, explaining, interpreting demonstrating whatever the feature we were talking about. Most often it could be a characterization. At times it could be some property variation, and all of these, a combination of all of these. Okay. So if somebody would like to want to go through more level of the fundamentals, I've given certain, referred to some of these. Some of these are books, some of these are, by the journals. They have a, for example, specialist periodic reports is a kind of report which comes every few years on developments of different techniques with some examples, etc. So all of these I have given, but you need to do more practice. Data available for each case. If you're looking at the thermal methods, TGA or DTA or DSA, a lot of examples, XRD, a lot of examples are available, a lot of data is available. For every other things, spectroscopy, microscopy, or analytical techniques, or anything diffraction, huge amount of data is already available in the literature, and they are all accessible. Data is there, and you can try to play with that particular thing. So I started the course with who will benefit from these lectures, as I mentioned earlier, the masters and the PhD students primarily, and on the industrial front, one can expect the scientists, chemists, and the engineers who will be using these and doing their characterization, purity levels, all of them. Okay, so as I already mentioned a while ago, lectures are based on the analytical, spectral, microscopy, and all these kind of techniques. So I've already covered all of those things. So started with atomic absorption, spectroscopy, and various things connected to that. Then went into the chromatography, of course, very surface touching kind of a manner, because this course itself is not fully on that, but nevertheless these are all relevant. From all these you get the materials, molecules, isolation, separation, then you look at the purity, all of those where you use variety of these things. So all these things have been discussed, debated. I'm just taking through kind of a traveling through that. So then at the end of each of the thing that I used to give, the practice kind of exercises, so that your knowledge, whatever you picked up, can be made a little better, strengthened, focused, and think in a better way. Okay, and also taken up the following that, the thermal techniques, primarily focused on the thermogravimetric analysis, differential thermal analysis, differential scanning calorimetry, and isothermal titration calorimetry, fully based on the principles, and explain the instrumentation in principal configuration, and huge number of examples, and some quantitative calculations also, and then qualitative identifications. So all of these have been, and some comparisons between these techniques, contrast or differences between these techniques, what information can be obtained, and all examples of both organic type, examples of both inorganic type, and all of these. Okay, in the polymer type, composites, real life examples I've used. So a lot of real life examples. So, and the biological examples too, and some materials which one makes for various purposes, that kind of things, and so some catalysts, clays, etc. Almost gamut of everything is being covered under that. So I recommend you to look at a lot of data available in the literature. Please practice a bit. Everyone does not need to practice everything. Those students who are working in a particular area can concentrate on that. That way you don't need all of them. Okay. So the isothermal titration calorimetry also have done, and for proteins particularly, and this knowledge enhancement exercise and all this. Then I took up electrochemical and electroanalytical techniques, explain all of these interfacial methods, etc., particularly this cyclic voltammetry in a full way understanding, and the reversibility, electron transfer reversibility, chemical reversibilities, all of these, and the sequential kind of reactions that happen, differential, and their mechanistic aspects of this, using that diffusion control, and some applications directly using the electrochemical parameter to quantifications of that. So all of those things, and some coordination complexes, their characteristics, their binding to the DNA, that means biological examples, and some examples of these the devices being built into that way, how redox potentials, organic, and in the biological bioinorganic side, how one can, and so all of these. So we have ran through quite a much of these ones. Then magnetic properties, we have gone through basic magnetic properties of the paramagnetic, ferromagnetic, antiferromagnetic, all of these kinds of things. How the susceptibility behavior with respect to temperature, etc. All these things have been dealt with, and magnetic susceptibility, magnetic moments, the inorganic complexes, the low spin level, high spin levels, all of these orbital contributions. These, and there are some exceptions to that, temperature, the populations of the excited state, how these ones. So all of these, and spin crossover, which is very important because the applications wise a lot of important, going from low spin to high spin, or spin to no spin and back, or something. These are the kinds of things you can do. Variety of those examples which are useful in storing the energies, etc., hard, soft magnets and the magnetizations, and these can be used in variety of systems. And then even into biological systems, in vivo things for the rats, applying towards the cancer therapy, is magnetic techniques that. So you can see the increase in the size, decrease in the size, all those kinds of things. So the gamut of things are there, which is shown over there, some examples for exercises. Then we have started the spectroscopy. As I said, all these kinds of spectroscopies, the light with the matter. So then initially we started with the electronic absorption spectroscopy, UV visible spectroscopy, and basic principle instrumentation configurations, etc. Then we started interpreting, of course, the deviations, etc., interpreting using various the selection rules, etc., of all these things. Their intensities, the bands observed, sometimes even the widths of these bands, sharpness of these bands, LMCT, MLCT, geometry variation, all of these, all DN systems that we looked at. And then we looked at a lot of examples where you apply these for various reactions, and how to identify from the absorption spectra the reaction taking place, complex is formed, all those kinds of things. Titrations to identify the metal ligand composition, and then some structural features, of course, you can. So variety of examples have been shown over there. You can also get their stability constants. When something is formed, when some complex is formed, there is stability. So several examples are shown. pKa determinations. So stability determination, complex formation determination, complex composition, whether it is 1:1, 1:2, 2:1, all these kinds of things. Then pKa determination and pH establishing, all that, metal ligand based ones. Then we have also looked at some biological systems like the iron sulfur proteins, rubridoxins, etc., those kind of examples. Then we looked at some nanocomposites too. So like these are silver nanoparticles, the size, shape, how it influences the absorption spectrum, a mixture of these species presenting, and from particularly these SPR band as a signature, its width, the multiple bands like the ones which are shown at these ones, where you have more than one type of a nanoparticle is present with the shapes, and their concentrations differ, etc. And the nanoparticle and their absorption dependence. Then we have also looked at the chitosan nanocomposites. Nanocomposites we have looked at. So some more nanocomposites with cobalt complexes, and then this is for the TiO2 with the Pani kind of a thing, absorbance. So how these their band gaps get affected, etc., with the bands, all of these, the band shifts, band gaps, all of these are at different loadings of the titanium dioxide into this polymer, polyaniline, that is Pani is polyaniline. So this also taken to the anti-cancer activity of some compounds, so AGO nanocomposites, etc., and then given some exercise for people to extend, elaborate, enhance their abilities to understand the things. Then having completed the absorption spectroscopy, then we went into the luminescence, fluorescence or emission spectroscopy and that. Okay, basic principle and the instrumentation, basic principle, various factors, and how this emission absorption or excitation emission, how they relate, correlate to that, like a mirror image, these kind of things are also. And what kind of a transitions lead to the fluorescence, all of those. Absorption, we know it is the reversal of the absorption, and what kind of a factors will enhance, what kind of factors will retard, means the quench, the fluorescence, all of these have been taught. Okay, then we went into the applications in the coordination chemistry, compound formations, ratio of the formation, geometry type. Suppose in some cases you may have a different kind of geometries, or in two different compounds, or in same compound different proportions of this. All these can be also identified from the fluorescence or emission spectroscopy, and they're all continued with that. And for sensing purposes, use the fluorescence as the technique on those, the MOF, manganese, metal organic frameworks, how certain species can be identified, in this case the TNT sensing, etc., various things, structural features of that, intermolecular electron transfer, fluorescence quenching in principle, and the copper complexes, how the photoluminescence depend upon the kind of the substitutions you have. This will change the whole spectrum going from here up to here, you see that. So whole range and entire thing is being monitored by changing these the R groups, etc. So that means you can tune these their emissions. So that means it is the fluorescence spectroscopy help you in building those kind of systems having diverse range of the fluorescence emission aspects or emission colors. Here is the stimuli responsive materials, etc. Then fluorescence energy, resonance energy transfer principle, some small molecular examples, some protein based examples, then application to nanomaterials, the fluorescence emission techniques to nanomaterials. So further nanomaterials, we have already had some excitation. You can see the fluorescence spectra, which is composite. So, and here other additional composites with the magnetic kind of the dots, the quantum dots, where one can use for the molecularly imprinting nanotechnology. So this can lead to the technology, and in analytical chemistry as well, simple, which will quantify the species present in all this. Okay, so then we took up or we entered into another spectroscopy domain, which is the mass spectrometry, which is quite different from all other, because it's a mass of the unit, a mass of the fragment, a mass of the molecule of that particular species, and that's what. So primarily focused on two techniques. One is the electrospray ionization technique, other is a matrix assisted laser desorption ionization. Both are very important in the inorganic compounds, which are very heavy molecular weights, as well as a lot of biological molecules and proteins and DNA, those kind of things as well. So basic principle, how at the principle level how it functions, what you will find in the spectrum, etc. Defined about the ions, molecular ions, what different kinds of molecular ions that one can expect. Not necessarily all of these kind of ions are found in all the spectra. Some of these are found in some spectra, etc. So that's where they are all given as a list. Then cisplatin, primarily focusing on the isotopic peak pattern, which is a very signature aspect to the mass spectrometry. Nobody should forget that. In the mass spectrometry, you are not just looking at the peak or the mass alone, but the identity of the species by looking at the this isotopic pattern. It's very characteristic. It's like a thumb impression, which will identify you as opposed to several million people. And so similarly, that particular compound compared to many other millions of compounds. Some coordination compounds, etc. Nanoclusters, nanocomposites, all of these, you can see that even replacing one of the gold by one silver, you will find exactly that. So not several, but one. Also you can find the difference very nicely. You can all do that. shuttling single metal atom into and out of the metal nanoparticle. As I mentioned, you take it out and put it in all the cases. Even one atom in a huge cluster, you can differentiate from that. Proteins and metalloproteins, SIMS. So all those things, very characteristic signature. You can tell that what metal ion is found in that, not a different kind of metal ion. If it is a zinc metalloprotein, if it is a copper metalloprotein, if it is an iron metalloprotein, you can exactly establish. There is no other technique to exactly establish that metal ion. You need to, in other cases, you need to do a lot more kind of things. Okay, so once you have the idea about all this, so ESIMS of paravalbumin, and you can also find different types of the ion cluster, sulfur clusters, oxidation states, all of these, molecular weight determination, etc. And then MALDI, we have, so MALDI principle, the instrumentation, what kind of a matrices use, and how you can measure or interpret the spectra, the metal bound, and even to go for the genetic engineering, essentially in that, where you can use the protein identification, like the sequencing of the protein. Okay, so protein sequencing, etc. All of these have been talked about. So you can then we have moved into EPR spectroscopy in this. Okay, and ESR, EPR, all those things. There is a huge range of applications are possible in that. So all these terms have been explained. Instrumentation, what is the basic splitting A value and the G values, how they influence their splitting patterns, etc. at various field strengths, X band, Q band, and W band. These are the major ones which are being used. So coupling with the neighboring nuclei, depending upon their I value, all of those things have been. So anisotropy in the G, all of those things. Then into the inorganic examples, and all these basic principles have been demonstrated using the inorganic complexes or inorganic clusters in metalloproteins, either way. So both ways, you have how iron sulfur clusters and these compounds interacting with the DNA, etc. Then some because EPR requires much more understanding of that, so therefore a lot more examples of organic and inorganic are given with this kind of things. So like how the splitting patterns, etc. happen. So this methyl radical, the CH2OH radical, you can see many other NH2 radicals, the even organic, these pi system, they're radicals, the naphthalide kind of an ion, which is ion, electron is added, inorganic complexes, all those things. So these are all some probes, etc. So all of these. So then we have photoelectron spectroscopy, explain how the surfaces, different kinds of things, etc. So part of this also will come into the microscopy technique when you impinge with electrons, photo emissions, photoelectron, gauging the principle, and the wide scan or survey scan, and of course the resolved scans here. So for organic things, I have shown various ones. As you increase the electron negative group by being bonded directly or away, how this spectral shift, the chemical shift change is all demonstrated for many things into the polymers, intercalated products, and trizine frameworks, all of those composites, etc. Those inorganic compounds, silicon based, and metal oxides, metal sulfides, metal halides, nanocomposites, so graphene based, and then heterogeneous catalysts, depth profiling, and various catalysis, following the catalysis, and all these things using, you can see all of them. Okay, so that's quite a range of applications. As the title goes, I've always given the inorganic, nanomaterial, both examples of that. A few cases some organic things come because to get gelled with the kind of system. Then Mossmeyer spectroscopy, here we have focused only on the iron system, nothing else, obviously. Of course, the compounds could be simple compounds of inorganic nature, or they are the composites, etc. So these are all basic principles, how to understand the phenomena, and what are the parameters influence, that is isomer shift and quadrupole coupling and the magnetic quadrupole coupling. So all of these kind of things explained, and using all these parameters, how you can explain your iron. See, the iron in general is found as iron 2 plus, iron 3 plus. There are many other oxidations there. I'm not saying they are not there. In iron 2 plus again you have low spin, high spin. In iron 3 plus again low spin, high spin. Totally 2 and 2, 4 combinations. All these 4 combinations simultaneously you can identify when they are present in the compounds in using only the mass Bayer as the. In other techniques you can identify, but you require a combination of experiments in those things too. So these are all explained, different compounds and various conditions, etc. Some natural systems. Okay, so all of these composite materials here you can see, and some dollar bills, etc., how they are there. Okay, then we went into the technique of extended X-ray absorption, fine structure, also Xane's near edge spectroscopy. Okay, so the principles, the way that it is, what are the terms, what is measured. So in the coordination compounds, basically you can get the primary coordination very well done. Of course you need certain compounds which can act as a kind of a model systems to fix the data and then get the metalloproteins. We have shown that. So exhausts for the metalloproteins, catalysts and nanomaterials. As promised, every technique I have taken to the nanomaterials, nanocomposites, etc. Examples are shown from all of these directions. Then NMR spectroscopy. NMR spectroscopy, I must tell you that is quite different from the proton NMR spectroscopy which one study for the organic compounds, because of the huge line widths that you have, and a lot of these compounds have got the odd electrons, inorganic compounds, and they also have the nuclei which are I greater than half. All these things making, and in the solid state itself they become very broad as compared to the solution, because in the solution you have a high homogeneity, and that homogeneity is lost in this. And most of the inorganic compounds you don't study in solution, you study in solid state surface, etc. So all of these are treated, so I'll go through a little bit quickly through these, and also given the methods by which you can resolve the data that is required and then establish the compositions of the different phases present in that and the structures present in it, all of these, using all those things, even extended examples into the proteins, and so all the paramagnetic type of compounds and the paramagnetic shifts, etc., all of these. Then we looked at the vibrational spectroscopy, both in terms of the infrared and Raman and inorganic systems. I'll just go through quickly the vibrations explained, and then instrumentation and all these ranges of that, where you can utilize all of these. And even for the proteins, we have given the examples of that. Okay, now then is the powder X-ray diffraction, basic principle, and different crystal lattices, Miller indices, all of these, powder XRD principle, what you measure, what is the data, how will you fit with that, and how will you measure the A value, how will you identify the lattice by using those things, etc. Everything worked. Auto indexing what, when, and how, and measuring the lattice parameters, all of these shown. And some examples with the powder for the composites, all these things by shape based and size based. Okay, and the last topic which I talked in the last few classes was on the microscopy side. As I mentioned to you that in the microscopy we have not looked at the optical microscopy, only electron microscopy, that is in SEM and TM, and scanning probe microscopy, that is in AFM. So all these things, basic principles, how one can follow it up for a host of techniques that are present with the SPM, scanning probe microscopy, and how it can be utilized, how the corresponding micrographs can be interpreted for various systems, both from the AFM and the TEM and the SEM. And in case of AFM, it is there is no electron beam is used, it is only some tip which touches, and there is a force between these things, and whereas in the electron microscopy, it is electrons which are bombarded at the sample and then get the structures and all kinds of informations that you can get for all this as we have talked. So what I would like to request all of you who is going through this particular course is that to please do certain level of practicing of these things for each of the technique. Whatever the technique you are more interested, whatever the technique you are doing for your project, master's project, or whatever the technique, whatever the research projects that you are doing for your PhD, the corresponding techniques you can try to focus and look at more depth. It is not possible for everyone to do for every case. I have totally shown 15 different techniques, the 4 analytical, 9 spectroscopy, and 1 diffraction and 1 microscopy. Okay, so it's huge for any one individual to do for all the cases the additional exercise to build in, but people can have certain portions of it which they are more interested, which they will be using a lot in their projects, in their research, in analyzing this compound, or in industrial R&D labs, etc. So with that, I wish everyone best of luck in understanding the subject on the analytical, spectral and microscopy applications of inorganic compounds and nanomaterials. Thank you very much.